Yeah, I want to talk a little bit about the research that we're doing in our group, and we're actually using the IBA data and really grateful that we have access to this great resource. And most of what I'm talking about here in this talk was done by my PhD student Adrian, who's also here today. Maybe raise your hand, yeah. Who actually, so I'm presenting in his stead today because we first weren't sure if he's going to make it, but he's here today. So talk to him if you have any more questions about it, or to me, of course. I'm also here. I'll briefly talk about the data, and I mean we've heard now a lot about the IBA data, but I want to present them a bit more from their spatiotemporal sort of aspects. And then I'm going to spend some time talking about the environmental predictors and why we choose them, and this is where Earth observation data comes in, and that we need spatially and temporally explicit data for these types of approaches. And then I want to introduce sort of the models that we tried in this project, and Adrian has tried about all models almost we could come up with, and but the main comparison here is sort of deep learning versus mechanistic models. So kind of the new deep learning approach compared to more sort of established, simpler mechanistic models. And then I'm going to show you some of our preliminary results, which are still work in progress. And this will mainly consist of showing maps of predicted richness throughout the country, similar to what we saw in the previous talk by Rob. And I also want to discuss a little bit sort of the ways forward. So what are the lessons learned so far, and where can we go with this line of research? So the very general setup, and I want to take you through this for a moment, is we have some type of biodiversity data, and let's say we have, this is actually the IBA locations, and we have for each location, let's just say we have a number that represents biodiversity. So a high number means a high species richness, for example, and a low number, a smaller biodiversity metric. And then we have a model at the very center of this. We train it on these biodiversity data, and the point of the model is to correlate these biodiversity data with the environmental metrics, so with data that we have on the environment, so that then we can go to the next step and use the model, the optimized or trained model, to make predictions, and for each pixel, preferably of Sweden, have a prediction of expected richness or whatever biodiversity metric one would choose. So I'm going to use this figure sort of as the central sort of guideline in this talk. So let's start with talking about the biodiversity data, and here we were looking for a data set that has good spatial coverage across Sweden, and is using sort of a standardized inventory method, and that the IBA data was the perfect candidate for this, even though preferably we would have even more sampling locations, but this is a great sort of data set for this proof of concept development of this approach. So this is the IBA data represented in a sort of temporally explicit and spatially explicit manner. So you can see that, I mean, as it was mentioned before, they're taking in weekly or sometimes monthly intervals throughout the year, and you can see by the size of the circles and the color of the circles, you can kind of tell how many ASVs were found in each of those traps at different times in the year. And we see, as we all know, there's low insect diversity in the cold months coming out of winter, and then it goes up, spikes up really fast, and you can kind of see this flux in from the south, sort of more northwards as the temperatures rise, as we also learned in the previous talks. So this is just the raw data, and you can already see there's some kind of interesting spatial pattern going on here throughout the year, and that's basically what we are after to really analyze and predict. So here just shown in a different graph. So here we have the weeks of the year, and then the number of ASV clusters, or let's just say species detected, and you see these green bars that represent most of the uncertainty, with some outliers going all the way up to 1,200. And then here just a different representation that shows the number of ASVs per sample, and you see that most samples taken at all these different locations throughout the year have something around 400 to 500 ASVs in one sampling session. And this is the taxonomic distribution that we've heard a lot about today already. So just want to be very clear here that the biodiversity metric that I'm going to be talking on from now on is the number of arthropod ASV clusters. And that's important to be explicit here because they are all possible biodiversity metrics one could model. And but yeah, then this takes me to the next chapter, which is the environmental predictors that we use. And this is actually where we spent quite some time in this project. And also Adrian, who has a background in remote sensing, has we've like looked into what type of data can we actually use that is both spatially and temporally explicit. And there are like different sort of general data sources. So we have climate data, for example, from WorldClim, that you can actually get for different times, for different years, and you can also get it spatially explicit. And then we also have data from Google Earth Engine. For example, there is a big data set on human impact that shows all the different infrastructures, like population density, light pollution, road network, and so on. We have data from satellite images that actually are updated daily and that we have free access to as researchers or in general. And for example, the Sentinel-2 system. And then we also have in Sweden, which is an especially exciting country to do this, we have this national airborne laser scanning data set. So this is a really, really dense cover of the whole country, producing these very detailed point clouds where you can essentially model almost every individual tree, if that's what you were after. But we use sort of derived data products from this that just show maps of tree height and maps of biomass that are the spatial rasters that we can plug into these models. Also, somebody needs me to indicate time if I'm going over time, because I just realized I'm not looking at the clock. Okay, so for any given place and time, we can essentially extract all kinds of variables from these data sources. For example, here an elevation raster. And now let's picture for any, if you give it a coordinate, this pipeline can basically extract all these different layers. So you have a multi-channel TIFF file that comes out of this. And this actually is a program that Adrian wrote. It's called EcoData Downloader. It's not not ready yet, but we're also working on sort of making this more user-friendly and publishing it. So if you're interested in these types of data, come talk to us. We'll be happy to collaborate. So here's some example of different features that were compiled, and I'm just going to move through it quickly here. So not going to go through everything, but the main point here is we have temporal resolution that differs between these different things. We have some that are updated daily. We have others that are updated in 5-day intervals, and others that are just updated yearly. And if it comes to the challenge of modeling insect diversity or any diversity throughout the year, we obviously want some predictors that have a temporal resolution that matches this modeling task. So, but we're using a mix of everything, because there's also value in using more static predictors that inform us, for example, about the elevational profile or the general tree height differences, even if it's not specifically for that month. I mean, it's not going to change much throughout the year, for example. Which brings me to the model. So the models that we explored, and actually let me skip to this one first and then I'll go back. So the most simple implementation would be something like a linear regression model, and that's also similar to what Rob showed. We have here ASV richness on the one end, and then we start optimizing the parameters in this model, and the predictors in this model could be things like tree height, temperature, and whatever else we compile. So then we have our set of sampling locations. Let's say here is a Malay strap, and then we can extract all of these different environmental predictors, and for example, for the center point where the strap is located, we can extract these values and start optimizing the parameters in this model and then make predictions. But now we saw the simple model, but now with the convolutional neural network model, for example, which is one of the ones we explored here, and that was kind of the original point of this project, we can actually use not only the center value or one simple numeric feature, but we can use sort of the whole contextual information at once. So instead of just saying the average tree height at the sampling point is 5 meters, we can actually say here is the whole raster of the surrounding tree height composition, and maybe the model can make sense of this. Maybe it can learn, okay, if it's at the edge of a forest or the edge of a certain size of cluster of trees, we expect sort of this certain number of species to occur there. So we similar with elevation and with human footprint index and so on. So we put all of this multi-channel TIFF file into the model, then have several layers of convolution and pooling, which reduces the complexity of these data. Then it goes into a fully connected network, and at the end what comes out is just single value. And this value is being, or the weights in this network are being optimized to match the training data as good as possible, and this value will eventually reflect the ASV richness that the model predicts for that site. So the advantage here is basically we can effectively use the whole contextual information rather than reducing it just to simple numeric features. So a potential advantage here. And we want to see, does it actually really hold up to the practical test and perform better than those other models? And that's what I'm going to get to now. So showing some of the results from this project. Sadly, and to our disappointment, so the CNN that we tested, it performed not significantly better than a random forest model, which is a much simpler machine learning model, or XGBoost. And well, compared to the linear regression, all these models are much better. But between these three, there is not a significant difference between their rooted mean squared error, or the mean average error, or the R2 score. So for context, basically these three models, they all work with just simple numeric representations of the predictors. The CNN works with the full sort of contextual information. So what does it look like actually when we put these models to the prediction task? So now we know how they perform, and they are decent in their scores. Could be better, but we also have very limited training data here. But we're also interested in what does the spatial pattern look like that these models predict. And so here are the predictions from the convolutional neural network that we tested throughout the year. And we see sort of a similar trend that also Rob found in his models. We get sort of like this influx of richness in the summer, and then sort of receding of this richness again. And actually, this is very spatially explicit, so we can really zoom in here and see very small scale patterns. I don't have what is the pixel size actually? Is it 1 kilometer or? Yeah, approximately 1 kilometer. But it could theoretically be made even more granular. This was just for computational reasons that we kept it at this. So the random forest model which looked similar in its performance statistics, it makes these types of predictions. And we see, even though it kind of performs just based on the performance statistics similarly well, it does a very different thing spatially here. So it seems actually like it's overfitting towards some of the maybe trap locations that had a very high richness, and then infers these whole sort of clusters of ecologically implausible high richness, right? I mean, we wouldn't expect there to be this very distinct block of high insect richness, and it seems to be a tendency of the random forest and also the XGBoost that we found that they infer these types of blocks when the numeric predictors that they have are very similar in those regions. So maybe we actually have an advantage here with the CNN model that it's a bit more, actually a little less sensitive to outliers, which often CNNs and deep learning networks are being referred to as there's a big risk of overfitting. But because there has been so much engineering that went into reducing overfitting of these networks, so there are so many tools one can actually apply, like early stopping of the training and using sort of dropout and lots of methods, that actually here we find they are, at least when we spatially analyze this, less likely to optimize toward these outliers. And then the linear regression actually does a very bad job here, maybe expectedly, because it's a super simple model. It doesn't really pick up even on the variation throughout the year that we have in the data. So this is basically, yeah, our results so far. Here we also split it up into different ecotypes that were in the annotation of the Malay strap data. And we see, for example, in some areas where, like the alpine areas, we have generally low diversity throughout the year, and both the CNN and the random forest model pick this up and correctly infer like a very different curve throughout the year for the alpine regions compared to, for example, cropland or forest. So these models really pick up the temporal variation, but throughout the year, and also the difference between ecosystems or ecotypes. But we don't really see on this example this like strong an outperformance of the CNN, or better performance of the CNN network compared to conventional methods. But yeah, the ways forward, so some limitations here are, well, we just use as ASV richness as the biodiversity metric. We've seen just some much niftier examples here earlier, for example, grouping them into ecologically similar groups. So that would be a natural next step to model not just overall richness, but model sort of taxonomic specific groups here. We also yeah, this is basically what I'm saying. Then a larger data set would actually be beneficial to demonstrate the potential utility of these deep learning networks, because just having these 200 locations, and many of them actually representing clusters of the same location, so effectively we only have like maybe 100 different places, it's very difficult to learn spatial patterns from such few calibration points. So we really need even bigger data sets. And here I think metabarcoding is a real promising tool, because it can produce data at scale, I mean, very quickly and fairly cheaply. So I think as more data sets become available with national coverage, or more gets added to existing data sets, this will be really, really good for these types of modeling efforts. And also I think we could look more into, I think that's also what Frederick was pointing at his last slide. I'm not sure if I understood correctly, but that maybe we need to look at complementary methods, not only Malay strap data, but there's also more insect fauna that is maybe not captured in the Malay strap. So what I'm talking about is, for example, additional samples like soil or water samples from the same sites. And okay, yeah. So here's just a project of my postdoc Belun in our group, who has analyzed these different substrates and basically found over 45 different locations that we get very different species communities. Especially we get much more Coleoptera, for example, in these other sample types compared to the Malay strap samples. And so just sort of as a hint that maybe more complementary sampling than only Malay straps would be even more beneficial to unlock insect richness across the country. Yep, that's all. Thank you.